So the next class of reactions is one in which we take an enolate and react it with an ester or an anhydride as the electrophile. The first reaction we're going to come across is known as the Claisen condensation. And the Claisen condensation is the reaction of an enolate with one of three things, either an ester, an anhydride, or we can even have the acid chloride. And this is going to give a functional group known as a 1,3-dicarbonyl. So the simplest reaction is one in which the two carbonyls are the same. So let's take ethyl acetate, and let's take another equivalent of ethyl acetate, and we're going to react this with sodium ethoxide. And the reason we use sodium ethoxide is because we need a base to form the enolate, but the ethoxide anion is appropriate because we have two ethyl esters and we don't have to worry about transesterification. So ethyl acetate is going to react with sodium ethoxide in the first step, and then in the second stage of this reaction, we're going to do a proton workup. And over the course of this reaction, we're going to get a 1,3-dicarbonyl compound. Now the 1,3-dicarbonyl compound we can think of this 1,3-dicarbonyl compound as being retrosynthetically coming from the enolate unit, which is an ethyl acetate, and some other carbonyl compound which can undergo a nucleophilic acyl substitution mechanism. And so that's kind of the idea with this Claisen condensation. And so the first thing that's going to happen is that we're going to undergo a deprotonation of one of the two ethyl acetates with sodium ethoxide. So let's say we take this carbonyl and undergo deprotonation. We're going to form an enolate. And then this enolate is then going to react with the second equivalent of the sodium ethoxide. And it's going to react via its carbon atom, because in the HOMO, that's going to be the largest lobe. And so this is going to be a nucleophilic acyl substitution mechanism. We get a new tetrahedral intermediate. Right, so that new tetrahedral intermediate has O-, ethyl acetate, and a methyl group. At this point, we get loss of the leaving group, and so we get collapse of this tetrahedral intermediate with loss of ethoxide. And we get this carbonyl compound. And this carbonyl compound can react with ethoxide immediately because that proton is more acidic. And so we're going to get a deprotonation to occur to give us an enolate, which is kind of just going to sit there until you work up the reaction. And when you work up the reaction with a proton source, you can, of course, get reprotonation of that central carbon to give you, as your product, the 1,3-dicarbonyl compound. And so this is the Claisen condensation reaction. Involves reaction of an enolate anion with an ester, anhydride, or an acid chloride to give this 1,3-dicarbonyl compound. And retrosynthetically, the 1,3-dicarbonyl is an important functional group to recognize because it can come in many forms. It could be a beta-keto ester, like this particular example, a beta-ketoamide, a 1,3-diketone. No matter what, it's still a 1,3-dicarbonyl compound in which you have two carbonyls in a 1 and 3 relationship from one another. next reaction is going to be the mixed Claisen reaction, or the mixed Claisen condensation. And this is really a Claisen condensation where the two carbonyls are not the same. Okay, so let's say we have a ketone as our starter material. So we have this ketone, and we're going to react it with, let's say, this carbonate, which is kind of like ester-like, right? It's got actually two leaving groups on either side. So I'm going to say it's ester-like. It will participate in nucleophilic acyl substitution. Okay, so we have two carbonyls that aren't the same, and we, let's say, treat this with potassium hydride. Potassium hydride is a base. And over the course of this reaction, we're going to get a mixed Claisen condensate in which we're going to place a new functional group, a 1,3-dicarbonyl, in the alpha position of where the ketone is. So again, the first thing that's going to happen here is we're going to do a deprotonation with hydride of one of these two protons to give us an enolate anion. Those are the only alpha protons that we have available to us. And so we have this enolate anion. The enolate anion is going to then react with the ethyl carbonate, diethyl carbonate, via a nucleophilic acyl substitution mechanism. Nucleophilic attack of that carbanion onto the carbonate is going to give us a new tetrahedral intermediate. And this new tetrahedral intermediate can collapse with loss of a leaving group. The leaving group this time will be the ethoxide. Right? So the only leaving groups that you have available are ethoxide, so ethoxide leaves. And then you get a new 1,3-dicarbonyl. Right, but again, this reaction occurs in two stages, so we have potassium hydride first, followed by a proton workup, because what happens is the ethoxide can come in and undergo a deprotonation of the now more acidic proton to give you another enolate. But then if you were to work it up with a proton source, you can reprotonate that center position to give you your, again, 1,3-dicarbonyl compound. And so again, retrosynthetically, this comes from a ketone piece here, where we have an enolate that could form, and some species here in which we have an ability to undergo nucleophilic acyl substitution. So you have to have an electrophilic center that has a leaving group attached to it. So these Claisen condensation reactions, whether it's a regular Claisen condensation or mixed Claisen condensation, can also intramolecularly. And this has a specific name for it, and that's the last reaction we're going to do, and that's known as the Dieckmann condensation. All right, so the Dieckmann condensation is just an intramolecular Claisen condensation. And we're going to start with this compound here. So we take this diester, and we're going to react this diester in the first stage of the reaction with sodium methoxide, a base. So a common feature here is that we need a base in order to do the deprotonation to give us an enolate. And finally, we're going to work up this reaction with HCl. The product of this reaction is a cyclic species that looks like this. Okay, so how do we get this, again, 1,3-dicarbonyl. But this 1,3-dicarbonyl is a little bit different because it's now cyclic. Well, again, the first thing that's going to happen is we're going to get methoxide to undergo a deprotonation. Undergoes that deprotonation to give you an enolate. That then is going to do an intramolecular nucleophilic attack to give you a tetrahedral intermediate that's now cyclic. This then collapses with loss of methoxide as a leaving group. And that's going to give you a 1,3-dicarbonyl compound. But again, you're under basic conditions, and so this proton then falls off by deprotonation with methoxide to give you another enolate. And this is the resting state of the product until you work it up with, in this case, HCl, to give you your product, which is now the 1,3-dicarbonyl compound. And so again, we can view this compound sort of retrosynthetically as being as coming from this piece here, which is our enolate-like piece, and another piece here, which is coming from an electrophilic piece, an ester. But we're forming that bond via an intramolecular Claisen condensation. So we're doing this in situ with the same molecule. And so this is the second type of electrophile that can react with enolates, and that's the esters, anhydrides, or acid chlorides.